To get this track fixed as fast as possible, they will bringing in a whole train full of fancy machines. A track renewal train, that's what it's called. Now, before this beast arrives, there's some prep work they gotta do. They might need to cut those old rails into smaller pieces and connect them with these things called fish plates. Loosening up the rail fastening system might also be on the menu. The new rails gotta be ready to go too, folks. They will get them delivered right down the center of the track. Then, welder crew will join these pieces together to make one super long, continuous welded rail, just like the name says. They have to put this new track right in the middle, exactly where the innovation train needs to go when it rolls out. This machine is basically a whole factory on wheels. It's got a bunch of different tools hooked together, all working in sequence. As the train crawls forward, it'll tackle the track renewal step by step, leaving a brand new track behind it by the time it leaves the area. Pretty slick, huh? Old sleeper removal. The first stage of track renewal is the removal of old sleepers. The releasing rail fastening system from the sleepers may be part of this process. Some machines integrate the semi-automatic clip releasing devices by hoisting such devices as part of the track renewal train to allow operators to manually position the device to each clip and trigger it to automatically release the clip. Some units have a machine to automatically remove spikes in the older type of wooden sleepers. After rails are untied from the sleepers, those old rails will be lifted up and pushed toward the sides of the train. The new rails are also fed in near the sides of the train in preparation to be inserted. The track renewal train has a machine that pulls the old sleepers out from the ballast. These old sleepers are delivered into the conveyors to move them out for storage at the rear of the train. The ballast bed is then cleared in preparation of laying new concrete sleepers. In case there is a need to lower the ballast bed, the ballast excavating process will be done. This process is integrated into the track renewal train in some models. Excess ballast in that case will be moved out through the conveyor belt to the ballast storage area. Those old ballast materials will be screened and cleaned to be reused. The unusable ballast will be kept in a separate storage to be discarded. There are gantry cranes attached to the top of the track renewal train. These cranes run along the special side rails of the train. These special rails also connect between cars, allowing operators to travel along the entire length of the train. The cranes are used to transport old sleepers into the storage area and bring the new sleepers into the working area. The new sleepers are delivered by the cranes to feed into the machine. The machine puts sleepers onto the ballast bed and spaces them to the exact position required by specification. After the new sleepers are laid, the new rails will be pushed from the side of the train into position on the sleepers. To prevent rails stressing due to temperature fluctuations during normal operation, the rail will need to be laid at a precise temperature, based on anticipated operating temperatures. After the track renewal train completes the tasks, the ballast will be put back on the track. For track renewal trains that do not have ballast excavating machines included, workers will use a shoulder ballast cutter machine that takes excess ballast that has been pushed out during the track renewal process into a screening and cleaning machine. The reusable ballast will be put back to the new track together with the new ballast materials. For track renewal trains that do not include track copying or leveling, a ballast tamper will be used to make final adjustments to the track to the correct specification. A ballast regulator will then be used to make the final shape of the ballast. Some track renewal train units have the ballast handling included, such that the entire process of shoulder cutting, cleaning, and placing of ballast is fully integrated. Thermite welding offers a mature and reliable method for constructing permanent rail connections. The process is known for its simplicity, convenience, and speed. It uses a special crucible filled with a thermite mixture of aluminum powder, iron oxide, and other metal additives. With a high temperature match, the thermite reaction ignites, generating intense heat that melts the mixture to form a molten alloy. The molten steel, being denser, sinks below the lighter slag, which floats on top. The molten steel is then quickly cast into a mold filled with sand. The aluminum in the molten steel acts as a filler metal, fusing with the rails as it cools, creating a permanent and high-quality weld. Alright, let's move on to the welding process itself. To ensure a strong and lasting weld, we've meticulously aligned and cleaned the rail ends. A precise gap is left between them to accommodate the molten metal that will fuse them together. For safety and proper flow, a mold will be clamped firmly around the joint to contain the molten metal during the process. Firstly, regulate the working pressure of propane and oxygen. Secondly, install the heater on the frame. Adjust the nozzle to the center of the send mold and place the shunt plug on the edge of the send mold. Remove the heater from the support and ignite the nozzle. Thirdly, regulate the pressure and mixing ratio of propane and oxygen to get the best flame. Finally, preheat for 5 minutes. The crucible fills with thermite, a dark, metallic mixture waiting to be ignited. A small puff of flame erupts at the top, igniting the thermite reaction. This reaction is fiercely exothermic, generating an intense heat that quickly melts the iron oxide within the crucible, transforming it into molten iron. The short-lived flame signifies the start and end of the chemical transformation, Within just 8 to 15 seconds, the fiery burst subsides, but the heat lives on. The molten iron is then carefully poured into the mold surrounding the rail joint, where an insulating layer keeps it hot and ready to do its job. As the metal cools, it solidifies, its strength fusing the two rails into a single, permanent joint. Finally, once cooled completely, the mold is removed, and the excess metal is ground away, leaving behind a smooth, seamless weld. Thermite rail welding has several advantages. Strong welds. Thermite welds are very strong and can withstand the heavy loads experienced by trains. Longitudinal continuity. Thermite welding eliminates gaps between rails, creating a continuous, smooth track which reduces wear and tear on trains and tracks, and provides a quieter ride. All-weather welding. Thermite welding can be done in all weather conditions. However, there are also some disadvantages to thermite rail welding. Time-consuming. The process of thermite rail welding is relatively time-consuming, as it requires preheating the rails and allowing the weld to cool. Skilled labor. Thermite rail welding requires skilled labor to ensure that the weld is done correctly. Safety hazards. The thermite reaction is exothermic and can generate a lot of heat, so there is a risk of burns if proper safety precautions are not taken. Snow creates a slippery surface, which can significantly reduce the grip between the train wheels and the tracks. This can make it difficult for trains to brake safely, increasing the risk of accidents. Hidden hazards. Snow can mask potential dangers underneath, like ice patches, uneven surfaces, or even objects on the tracks. This can make it harder for train operators to see and avoid hazards. Because of these dangers, railroads take steps to clear snow and de-ice tracks during winter weather.
I wonder what that's seeing. That's okay.
Automotive railway snowblower can be turned by a turntable located at the lower part of the machine. This enables quick direction change of the snowblower. The 1500 horsepower blower engines enable snow to be ejected up to a distance of 40 meters and at a volume of up to 16,000 tons of snow per hour. The scoop wheel housings are equipped with chutes which can be swiveled separately by hydraulic cylinders. Two halves of the stem are retractable via a stable sliding frame by extending the stem halves and raising the constricting plates. The snow clearing width can be increased from approximately 3,000 to 5,800 millimeters. Each discharge chute has a hydraulically operated launch flap, through which the snow spray can be directed if a higher snow removal load is required. The blower equipment speed is set to a slower level if a spray distance is required high. The speed of the blowing device increases. In operation, the cab can be fully heated, and there are two large heat exchangers with fans in the floor area if the vehicle is not in motion or extra warmth is required. The windshields and rotating panes are made of 14 mm laminated glass.